Hi there. Welcome to the Chapter 1.3 worksheet from Stevens's Matrices, Vectors, and 3D Math. In this worksheet, we're going to investigate the same three systems of equations that we saw in the worksheet from Chapters 1.1 and 1.2. When we did this in 1.1 by hand, we solved these by hand, and for the first system, we got a nice unique solution. For the second system, we had no solutions. And for the third system, we had infinitely many solutions. Right? And when we did this in 1.2, we set these up as matrix equations and used the backslash command. And when we did this with the first system, it worked great. We got the same answer as we did by hand. When we did this with the second system, where there was no solutions, it actually gave us, so the MATLAB gave us an answer. It did spit out a warning message, but it gave an answer which was not an answer at all. And then in the third situation, MATLAB spit out an error and it said that it could not do that. The system could not be solved. So at least in that case, it recognized there was a problem, but on the other hand, there were infinitely many solutions, and it returned the answer of no, there are no solutions. So when you run into the situation of no solutions or infinitely many solutions, the software doesn't necessarily get you out of the weeds. So we're going to see if we can't ahead of time determine whether or not we'll have a problem, and you can do that by checking the determinant of a matrix. And so we're just going to check the determinants and calculate the inverses of these three systems, or the matrix versions of these three systems. So if we look at this first one, we have a coefficient matrix of 1, 0, negative 3, 2, 2, 9, and 0, 1, 5. And I've already put these into MATLAB. There's a little program I wrote that just, it's a file that contains these matrices. So they're already in here. So if you look at A1, that's the coefficient matrix for our first system. If I look at the determinant of A1, I get a determinant of negative 5, and that's the same answer you would get if you calculated the determinant by hand, expanding across one of the rows or columns. So, since the determinant is not 0, it has an inverse, so let's check that inverse. Inverse of A1. Perfect. No errors. Everything's fine. We can get a solution using the backslash command. We're looking good. If, on the other hand, we go to this second system, which has no solutions, if we set that up as a matrix equation, the coefficient matrix would be 0, 1, negative 4, 2, negative 3, 2, 5, negative 8, 7. And I already put that into MATLAB. So let's take a look at that. A2. And if we check the determinant, by the way, if you check the determinant of this matrix by hand, you will get 0. But if we do it in MATLAB, we get a little bit of round-off error. And what that means is that the determinant is not identically 0. It is 2.2 times 10 to the negative 15. It's very small. It's about machine 0, but it is not, a pure 0. So that means we can check the inverse. So let's get the inverse of A2. And it spits out an error message, which is good because we know the determinant is 0 and it should not have any inverse. But it does in fact calculate an inverse because the determinant was not quite 0, so it gets an inverse. And when you first look at this inverse down here, it looks like some nice normal numbers. But what you need to notice is that this entire matrix is multiplied by 1 times 10 to the 16. So that is a huge number. This is a matrix of huge numbers, right? And that's a result of, in the process, eventually dividing by values very close to 0. So that's a problem. There is no inverse, but it produces one. It's a weird one, but at least you get an error message. If we look at our third system, this had infinitely many solutions. We take the coefficient matrix, which would be 1, 6, 2, 1, 0, 5, and 0, 1, 2. Put that into MATLAB, which I did earlier. So A3 if I look at the determinant, and if you calculate the determinant of this matrix by hand, you get 0. And we saw that MATLAB won't always get that exactly, but in this case, it does. The determinant is 0. So that's good. MATLAB spotted it. There's no round-off error. And so if you try to get the inverse of this matrix, inverse A3, notice it spits out a warning. Matrix is singular. To working precision, singular. Right? Remember, a singular matrix has no inverse, and a non-singular matrix does have an inverse. It's worth being familiar with this terminology because it gets used regularly. I know it's not exactly clear why they call it a singular matrix, but it gets used quite often. So singular means no inverse, and that is demonstrated here with an answer which just has a bunch of infinities, and again, that's a result of dividing by 0, essentially. All right, so this was at least able to tell us ahead of time whether we've got a problem by just looking at the determinants. Determinant of A1 is -5. We're good to go. The determinant of A2, that's crazy small. We should be very careful. And the determinant of A3 is 0, and we know we should not try to use the inverse. So that's how we can get a preview of whether or not we've got a problem. And if we do have a problem with either a determinant that's crazy close to 0 or 0 identically, we know we have to investigate further, and that investigation might entail solving these systems by hand. Right? So the software doesn't completely save us, but it can certainly help out to determine when there's a potential problem, and if there aren't any problems, then it does a great job of solving the system. All right, so that wraps up Chapter 1.3. I will end it here. We'll see you at Chapter 1.4 if you are so inclined to join us. Okay, bye.